Hello everyone, welcome back to the channel. I hope you all are doing great. So we were discussing about our previous year questions of the UPSC geoscientist exam, and in that we have started with our organic chemistry portion. Right. So the first two parts we have already discussed about these particular series. In that, in the first part we have discussed about our first 30 questions. The next 30 questions were discussed in the part number 2. Now this is gonna be the part number 3 of this particular series. If you have not watched that particular part, I'll provide you with the link to that in the description. You can have a look from there. Okay, so let us begin with our part number 3 now. So before starting the video, if you are coming to the channel for the first time, make sure you subscribe to the channel and do hit the like button also for the video if you understand the concepts, and do share it with your friends as well. So let us begin with the part number 3 now. The first question, that is your question number 61, because 60 questions already we have discussed. So this question is there on your screen, so you can try it firstly yourself. Okay, so I'm proceeding with the solution now. So here a reaction has been given, an alkyne species is given to us basically. The two of the different reagents have been passed, resulting into the formation of the two different products. That is your X and Y. We have to predict what is this X and Y species getting formed. Okay, so this is my alkyne species. Right now, here in the for the product formation, that is your X1. Here the reagent that is passed is the hydrogen in the presence of the palladium barium sulfate. This is being passed, and this is called as a Lindlar's catalyst. This is my Lindlar's catalyst. Now whenever we have the alkyne species and they are treated with your Lindlar's catalyst, it results into the formation of the alkene species, right? So alkene, that is basically a cis alkene, has been formed over here. That means this alkene species will be formed, and the substituents, which is your methyl substituents, they are present upon the same side. So this is gonna be your product number, product X over here, right? Whereas in the case of the Y product formation, the reagent that is passed is the sodium in the presence of the liquid ammonia has been passed. This is called as my Birch reagent. This is my Birch reagent. So when we are treating an electron-rich species, basically your alkyne over here, it is treated with the your Birch reagent. It results into the formation of the radical anion species. So like this, an alkene species is formed, and here on one of the carbon center there is this radical is being formed, and other side this anionic species is being formed. So both of these, they are my electron-rich species are present over here. So if they are present close enough, there will be lot of steric hindrance. So these two anionic species, that is your radical and the anion, they prefer to be a further apart distance from the one another. That means we get as this type of the species. Here on the one side this radical species, and other side this anionic species is being present, and the remaining substituents are present like this. So due to that, it results into the formation of the trans conformation over here. Further on the workup, if it is being done on the presence of, because of the liquid ammonia presences they are being there, it will provide you the protons from there. Okay, so an alkene will be formed, that is of the trans conformation like this. This one will be the product Y over there. Okay, so now let us take it from our options. The option A, it says that both the methyl substituents are present in the trans conformation in the X substrate. So this is not your correct option. In the option number B, the X, it says both the methyl substituents are on the same side, and the Y, it says both the methyl substituents are on the opposite side, and this is what we wanted. So the correct option for this particular question will be the option D over here. Okay, so this is the answer to this particular question. Now let us move upon to our next question. That is this one. So here it is saying that which of the following chlorides it undergoes the fastest SN2 reaction. So nucleophilic substitution reaction, that is of the second order, is being carried out on all of these particular substrates. We have to predict in which of the cases the fastest reaction we are going to observe. So in the SN2 reaction, what happens is you have, suppose this is your alkyl halide species, it is present, the nucleophile it comes, and this is the sigma bond and this is gonna be its sigma star. So what happens is this nucleophile from the back side, it gives an attack over here, and this X group it leaves from here. Both these processes takes place simultaneously, resulting into the formation of this type of the intermediate stages like this. Here the nucleophile, this bond is forming and this bond is breaking over here, right? And finally what is going to happen, the nucleophile will be attacking at this particular site and the X negative will be leaving from here. So there will be inversion in the configuration. You are going to observe this, right? So in this, what you observe is that this transition state that you have got it, this is the transition state. This transition state is basically an electron rich transition state. Okay, just a second. This transition state that you are getting, it is your electron rich in the nature. So what happens is, if in the adjacent you are having some of the electron withdrawing groups, at that point your SN2 reactions, it will be the fastest one. So my transition state is electron rich in the nature. So through the MOT approach, you can get a better understanding of this when we'll be discussing about the reaction mechanism. There in detail we will be discussing about this. Okay. So for the while, you can just see that it is, if it is your electron rich species, if on adjacent there is presence of the electron withdrawing group, so the rate of the reaction for the SN2 it will be increased over there. Okay. So among these substrates, you can see that in the substrate A that I am having, the carbon center on which the SN2 reaction it is gonna take place, in the adjacent position is my electron withdrawing group, right? So that means it is gonna stabilize my transition state. Whereas in the other molecules also, you can see in the B molecule, on this carbon center the attack is gonna take place. In the adjacent I am having a phenyl group. That is, through its electronegativity nature, it can to somewhat extent it can stabilize the transition state. In the C molecule, if I see, and this carbon center, the attack will be taking place, and here is this alkene species which can, so to some of the extent, it can stabilize the transition state. Whereas on the in the molecule number D, molecule D, here on this carbon center, the attack will be taking place, and this is the oxygen that through its inductive effect it can stabilize. So maximum stabilization you are going to observe in the substrate A that is present because of this carbonyl group which is attached over there. So that means the fastest reaction for the SN2 attack you will be observing in the A molecule. Okay. The correct option is the option A for this one. I hope this one is clear. So now let us move upon to the next patient. So here it is there. So in this, what they are saying, again a reaction has been given. We have to compare the order of reactivity of this HX species. So what basically is happening over here? We are having is an alcohol species, and this is treated with the HX species, right? So here what can happen? This oxygen that is containing the lone pair of electrons, it can abstract the H positive from here, and this X group it can leave, right? So it will result into the formation of this particular molecule. Right? Now the water molecule that has been formed over here, it is my good living group. So this reaction, it can proceed on two of the paths depending upon the R substrate that we are having. If my R substrate is my suppose primary alkyl species or the methyl substituent it is present, the reaction will be proceeding through the SN2 path, right? Whereas if our R group is our tertiary alkyl species or some benzylic species that is present, whereas stable carbocation formation can be done. This is gonna proceed through the path that is through the SN1 reaction. Okay, so the main thing is, so this is dependent upon the substrate R, this path which is gonna be following over there. But you can see in the initial step, the breaking of this HX bond is important because this is a step that is giving us this particular substrate on which the further reactions are going to be proceeding, right? So that means faster is this breaking of this FX bond, it will take place, more faster the rate of the reaction it will be there. And we know that for the HI, the bond is the longest one, followed by the HBr, and then is the HCl. This is gonna be the order of the reactivity because HI bond, it is the weakest bond. It is the weakest bond. The more is the weakest bond you are having, faster is gonna be the rate of reaction. So this is gonna be the order for this particular reaction. So here you can see in the option A, this correct order has been given that HI is greater than HBr and then is for the HCl. Okay. So the correct option is option A for this one. Let us move up on to the next question now. So this is the one. So here now different substrates have been given, that is different isomers of the 1, 2, 3, 4, 5, 6 hexachlorocyclohexane molecule has been shown. We have to predict which of these it undergoes the E2 elimination most slowly. Oh. So each of this substrate that is given to us, we can convert it into the chair conformation and we'll be having a look that on which position this Cl groups are present to one another. Okay, so the molecule number A, if I see, this is the one, right? So here this Cl, this is number 1, I am labeling it. So this is present in the red side. That means it is present in the above field. Next Cl, this is also present in the red side. So that means it is present in the above side. The again the third carbon, this is present upon the red side. So this is the one we are gonna have it. Now on the next carbon, this is present in the dash position, which means it is present in the downward side, it is present, right? On the next carbon, it is again on the red side, so this is the one, right? In the sixth carbon, again it is present on the dash side. So this is the substrate that we are getting in this particular molecule. Okay. Now let us draw for the second molecule also, where all of these Cl groups are present upon the wedge side, right? So this is the molecule, it will be looking like this one. All the Cls are present on the wedge side, that means all are present on the above direction, like this. Above side, it is present, above side. Here also this is on the above side and here also this is present on the above side, right? In the molecule C, if you see, they are present on the adjacent side, they are present above and the below directions, like this. This is the one. So here this is present on the above side and this is present on the below side, right? In the third case, it will be present in the above side, then in the bottom direction. Again in the above direction and then in the bottom direction. This is the substrates we are getting, right? Next, in this particular molecule, it is three of them, they are in the above direction, that is in the wedge position you are having, like this one, the above direction, and then three of them, they are present in the bottom direction. So this is gonna be the structure of all of these molecules. Among these molecules, if you focus upon the molecule C that you are having, here you can see all the groups that are your Cl groups, they are present upon the axial positions. Here this is at the axial, this is also at the axial, this is also the axial position. All of these molecules, they are present at the axial position. And when all of them they are at the axial position, you are going to observe the slowest rate for the dehydrohalogenation reaction. Okay, because we want the dehydrohalogenation. That means there should be the loss of hydrogen and the halogen molecules. Like the HCl, it should be lost from here. But here in this particular case, if you see all these groups, since they are on the axial position, so here for the elimination to take place, the groups should be anti-periplanar to the one another. Like this, here it should be the hydrogen, and on the next carbon, if there should be presence of the hydrogen atom, there should be an angle of the 180 degrees for this elimination to take place. If you focus upon this particular molecule, this is the carbon center, you can see, on which the Cl group is present, the hydrogen atom. It should be present on this particular axial side for the elimination to take place. But in this case, the hydrogen atom will be present in the equatorial position. So that elimination, it will be difficult. In the other cases, if you will be seeing, for the first molecule, if you observe, for this particular chlorine atom, this is present at the axial position. The hydrogen, it is present at the anti-periplanar position, and this can easily be lost from here. Like this H positive can be lost, this electron density will be transferred, and this Cl group, it will be leaving from here. So the slowest rate we will be observing when all these groups, they are present on, all the Cl groups are present upon the axial positions. Okay, I hope the reasoning is clear to you. So the correct option will be the option C over there. Okay. So now let us move upon to the next question. This is the one. So here they are saying a reaction has been given. We have to predict which type of elimination reaction is carried out. So here in this substrate, you can see there is a presence of this NO2 group and my OAP. Now this NO2 group that is present, it is a strong electron withdrawing group. And OET that is present, it is not a very good living group. Because for a living group, it should be, so these are the two of the conditions that you should remember for the living group. Either the living group, it should contain the vacant d orbitals, vacant d orbital in it, vacant d orbitals in it. Like you can see, you have the Cl group, Br, I negative. All of this, they are my good living groups. These are present, right? And the other condition for a living group, it should be that there should be presence of the resonance in it. Like you can see, this is a resonance. Resonance. There should be presence of the resonance in this. Example, you can see in the OAC molecule that you observe, that is your OC double bond OCH, 3 species. So here O negative it is present. This negative charge is involved in the conjugation with the adjacent carbonyl group. That is why it is your good living. Whenever you have the second period anionic species like the OH negative, or you observe the OET negative, these are not very good living groups because there is neither they have the presence of the vacant d orbitals in them nor they contain the resonance in them. So they are not a good living group. So some push has to be provided to them so that these species can leave from the molecule. So what we do is generally we treat this OH species with the water like this H positive in the acidic medium we are providing. So with that what happens is basically your OH negative gets converted into the water, or your OET negative also it is treated with the X positive, so it will be converted into the ethanol. Now these are becomes your neutral species, so that is why this water and ethanol can leave from the medium, but your OH negative and OET negative is not a good living group. Okay, so in this substrate we are not having a good living group, right? So how is the reaction gonna be proceeding in this case? So you will be seeing this. I'm drawing this substrate over here. This is the benzene ring I'm having, and along with that this ring is present, and here is this NO2 group, and here is this OEP group, and here along with that there will be presence of the hydrogen atom also, and there is this double bond. So how is the reaction gonna be proceeding? So this base that we are having, this base, it will come and abstract this acidic proton. This proton, it is acidic because after removal of this H positive, the conjugate base that is being formed is highly stabilized. You can see the species. Here the OET negative is present. Here you have this NO2. So here the negative charge that is getting being formed, it is highly stabilized because of the presence of this NO2 group, that is my electron withdrawing. Also you can see there can be the conjugation due to this alkene species that is present over here, right? Now in the next step what is going to happen, this negative charge electron density it will be shifted, and this leaving group it is now going to leave. That means and some push we are providing it from the side, and then this leaving group it is able to leave from the medium. That is going to result into the formation of the alkene species like this. Here this double bond, here also, and here will be this NO2. So the desired product you are reaching it through this one. So here you can see what mechanism will be followed is firstly the base is abstracting an acidic proton resulting into the formation of the conjugate base. This is my conjugate base is being formed. So whenever the elimination reaction is going firstly through the formation of a conjugate base and then the elimination is taking place, this is called as the E1CD mechanism. Okay, the correct option will be the option C for this particular question. Okay, now let us move upon to the next question, that is this one. So here they are saying that which of the following statement is true for the given reaction that has been mentioned below. A reaction is given, you have to choose the correct statement. So what is basically happening over here? We are having an alcohol species, acidic medium is given, and the alkene species have been formed over here. That is after the elimination is taking place. So how is basically the reaction proceeding? So this is the CH3, here the OH group. Again, you can see here the OH group that is present, that is not a good living group. So to make it into a good living group, this acidic medium it has been provided over here through the H2SO4 source. So what is gonna happen? This oxygen atom contains the lone pair of electrons. This will abstract this acidic proton. So you can see here will be the formation of this OH2 and this will carry the positive charge because oxygen has donated its electron density. Now you can see here this carbocation formation is visible because after the release of this water we will be getting is a tertiary carbocation. So at this position you are having is a stable carbocation formation, that is my tertiary carbocation. So that is why the reaction can proceed through the even elimination path, right? So tertiary carbocation is your stable one. Now this further it is gonna give us the elimination reaction because no further species have been given, that nucleophile species is there that can attack over here, so elimination will be taking place. So here is the presence of this alpha hydrogen, and also you can see this carbon atom it is present, that is your alpha hydrogen. This one is also there, but that is these two ring species they become to be the equivalent one only. So if the hydrogen from the ring we are removing it, this substrate we are getting ring formed, that is here this alkene species, and this methyl substituent will be present, and if from the methyl this H is getting being removed, we will be getting is this alkene formation over here. Here it will be double bond and CH2. So among these two we have to look the one that is the major product. So the more substituted alkene that is in the path number A that is there. So this is the more substituted alkene. More substituted. Okay. So this is my more substituted alkene. Substituted alkene. And more substituted alkenes they are called as my Zaitsev product. So this is my Zaitsev product. Okay. In the other case, if you will be seeing, this is gonna be the minor product you will be observing because this is your lesser substituted alkene you are getting into it. Okay. So we can say that my second is gonna be the major product and one is gonna be the minor product, and this one that is your second one, this is called as the Zaitsev product, right? So second one is the major and it is your Zaitsev product. You can see this is given in the option number C, that is second is the major one and this is your Zaitsev product. So the correct option it becomes the option C over here, right? So now let us move upon to the next question, that is this one. So here they are saying which one of the following alcohol it dehydrates the fastest when it is heated with the acid. So again the alcohol species have been given. It will result into the formation of the carbocations. The one in which there is a maximum stable carbocation formation we are having, that is gonna give us the fastest rate of the reaction. So you can see that OH, imagine in all of these cases it has been protonated and it is leaving from here. So this will result into the formation of the carbocation, that is this one. Here this carbocation will be formed, right? In this case the carbocation formed will be at this position, that is CH3, and here will be this positive charge it will be present, and here you will be seeing this CH2 positive it will be formed over here, right? In the D case you will be seeing that at this particular site the carbocation it will be formed. So we know that there are various electronic factors that determines the stability of the carbocations, right? So in the first case, you can see that this particular carbon center on which the cationic species is being formed, it is further attached with the two carbon centers. So this is my secondary carbocation. This is my secondary carbocation, right? In the second case, if you see this carbon on which this positive charge is present is further attached with the 1, 2 and 3 carbon atoms. So this is my tertiary carbocations. This is my tertiary carbocation, right? In the C molecule, if I see this carbon on which the positive charge is present is further attached with the 1 carbon atom only. So this is my primary carbocation. Primary carbocation. Okay. Now in the D molecule, if I see, there is this positive charge carbon and this is attached with the 3 carbon center, and along with that there is presence of this double bond presence also it is there. That means it is my allylic carbocation, and we know that the allylic carbocation, they are the maximum stabilized one, right, because of the resonance present between them. That means first is dehydration, it will take place in the molecule D over here, right? So this is how you can solve this question. So now let us move on to the next question, that is this one. So again a reaction has been given, we have to predict the product for this reaction now. Okay. So the substrate we are having is this ring is present, and here is this double bond. Now this is firstly treated with the bromine. So bromine, when it is treated with the alkene species, we can write the bromine like this one. Okay, so Br and this Br. So what is gonna happen? This alkene electron density it will be shifted, and this Br is gonna leave from here. So this will gonna result in the formation of the brominium ion over here. So here it will be a positive charge along with the release of your Br negative ions. Right? Now you can see there is a presence of this oxygen atom that is having the electron density, so it can provide this type of the NGP effect, you can say, that will gonna release the strain from this this brominium ion ring that has been formed over here, right? So this is gonna result into the formation of this particular species. So here you can imagine that this is coming, this brominium ion ring is being formed in the wedge plane because we have to consider our stereochemistry. So here we can say that this Br group it will be opening and this will be present on the wedge side. So now here the oxygen will be carrying the positive charge because it has donated its electron density. Right. Now in the next step what is gonna happen? We have added the methanol to at this side. Right. Now you can see we have to look upon to the stereochemistry for the attack. So here we have assumed that the bromine is present on the wedge side. That means the front plane of this particular molecule is already blocked by this PR group. So now this methanol will be attacking from the below side and will be attacking over here and neutralizing the charge of this oxygen atom. So we will be getting this particular species. Here the Br group is present on the wedge plane, and this OMe group that has attacked over here, this is present at the dash position. So methanol here the H will be also present. Further you can say this H positive it is lost from here like this one. So our final product will be Br at the wedge, and at the dash position the OMe group it will be present. So from this you can check your options. So I can see it is the option number A only, where the one of this group is present at the wedge and other one is present at the dash. We could have also considered that the brominium ion is formed at the dash, then methanol group will be attacking from the above plane. Okay, basically opposite stereochemistry it will be there because of the strain. One of the side it is getting the blocked. Okay, so this is the answer to this particular question. So now let us move on to the next one, that is this. So here they are saying that which of the following alkenes will react most readily with the concentrated sulfuric acid. So various alkenes have been given and the acidic medium is being provided. So whenever this alkene species we are having and we are treating it with the H positive. So how is the reaction going to proceed? So this by electron density it will be shifted on one of the side of the carbon atom. You can say like this. On this carbon center we can say that this has shifted. Now this carbon which is electron density will be abstracting this particular proton. So here what is going to happen? It will result into the formation of the carbocation on the other carbon center. So here it will be now methyl group it will be formed. So this carbocation species is being formed over here. Now in the molecule B also B, C and D similar manner we will be seeing the various carbocations that are being formed, and fastest rate of the reaction we have to predict, right? So for the fastest rate the maximum stabilized carbocation it should be formed. So in the first case, the carbon is attached with the one carbon atom, that is the carbon bearing the positive charge is attached with the one further carbon atom. So this is your primary carbocation. Right. Now in the second case, that is the B molecule, here I am having this carbon, here this methyl group, here the double bond, and this CH2 it is present. So here this H positive. So we want the stable carbocation to be formed. The first case it will be symmetrical, so either side the same carbocation you will be getting. But here, if you shift the electron density on this particular carbon center, you will be getting is the maximum stable carbocation formation. So on this center, the positive charge it will be formed, and here it will become the CH3. Right. So now this carbocation that we have got, this is attached with the three methyl groups. So this is our tertiary carbocation. Right. In the C molecule now, in the similar manner, we can see which carbocation. I am drawing it over here. This is carbon. Now here this is attached with the two Cl groups. Okay. And here is this carbon attached with the two Cl groups on this side as well. So here this H positive, when it is coming on either of the sides, you can shift this. So this is gonna result into the formation of the carbocation that will look like this. Here the positive charge it will be formed. Here the carbon, one hydrogen atom, and the two Cl groups it will be present over here. So now we can see that here there is a presence of this Cl group on the carbon center that is containing the positive charge. So this one is gonna be highly destabilized carbocation because this Cl group that we are having, they are gonna apply the minus I effect because of their high electronegativity. So it is highly unstable carbocation. Right. Next in the D molecule, if you see, again there is a presence of this CF3 group and there is this methyl group at presence you are having it. So we can say that the electron density, we can shift it on either of these sides. So if I'm shifting it on this particular carbon center, here you will be getting is CF3, CH, here the hydrogen it will be attacking and here it will be CH and this methyl group it will be present. So here is the positive charge. So again you can see, though this carbon center on which the positive charge it is coming, it is attached with the two carbon centers, but there is a presence of the CF3 group which can apply the minus I effect over here. So it is gonna destabilize my carbocation. So we can say that among this all of the four cases, the maximum stable carbocation is formed in the second case where the tertiary carbocation formation it was taking place. Right. So that means the answer to this particular question it will be the B option because we have to look at in which of the cases most rapidly the carbocation formation it is gonna take place. Okay. So B is the correct option for this one. So now let us move on to the next question, that is this one. So here they are saying the regioselectivity of the electrophilic addition reaction of the HOCl with the propene. So propene is basically CH3, CH and here the double bond CH2 you are having. This is your propene molecule and this is treated with the HOCl. HO and the Cl group. This is the substrate they have treated, reagent that they have used over here. So among these two, you can see that oxygen and the chlorine, oxygen is more electronegative. So this is gonna carry the partial negative charge and the Cl it will be as compared to the oxygen it is less electronegative, so positive charge it will be coming. So this is the Cl positive group that we are seeing, that this is gonna act as my electrophile. So now this electron density it will be shifted and will be abstracting the Cl group and this OH negative it is gonna leave from the medium. So this is gonna result into the formation of a three-membered ring, like the brominium ion only, the reaction brominium ion is getting being formed, where the chlorinium ion you can say it is being formed over here, CH2. Here you will be having this Cl and this is gonna carry the positive charge over here. Right. So this is gonna be the substrate you will be getting. Now in the next step you will be seeing the attack of the OH negative side. So OH negative will be attacking on this particular side and this Cl group it will be shifted over here. So basically we have to see the stability, this carbocation formation over here and not this OH negative. So we want that the stable carbocation should be formed over here. So we will be getting is this particular carbocation formation, CH2 and the Cl it will be present, and here will be the presence of this positive charge. So from the options you can check your answer. So here it will be the first case only I can see CH3 CH positive with the CH2Cl. This is the carbocation species which is being formed over here. So this is gonna be the answer to this particular question, right? So main thing was just to we have to look among the oxygen and the fluorine, which one is gonna act as my electrophile and which one will be attacking as my nucleophile. Okay. So now the next question that we have is this one. So this question it says which of the following products is formed when bromine adds to the anthracene? Anthracene is our three of the benzene ring have been fused like this one. So like this type of the substrate we have it. So on this we are adding is the bromine. Br2 is being added over here. So in the anthracene if you see the center ring that is present, it is the most reactive ring. This is the most reactive ring. That means addition of this Br it is gonna take place around this particular, in this particular ring it is taking place. The final product that you will be getting, it is gonna be this one. So both the Br group that is present, they will be attached at the anti position to the one. So this is gonna be the product. Okay. The correct option is the option D over here. Right. So now let us move upon to the next question, that is this one. So a reaction has been given that is taking place in the various steps it is basically taking place. We have to see that which of the following steps we have to follow. Okay. So firstly we are having this benzene ring that is present like this. On this particular benzene ring, they are attaching is one chlorine group and other is the ethyl substituent is being present over here, right? But it is at the meta position. So whenever this type of the substrate we have to predict, because this chlorine group that is present, it is also my ortho para directing in the nature. This is my ortho para directing. Also this alkyl group that is we are having, this is also my ortho para directing in the nature. That means whether firstly if we are if we are doing the chlorination of the benzene ring and then treating it with the alkyl substituent, it will come at the ortho or the para position. Or if firstly the alkylation we are doing, that is Fredel-Crafts alkylation, and then we are treating it with, we are doing the halogenation of it, that is chlorination. So that group it will also come at the ortho or at the para position. But we want it to be coming at the meta position. That means some electron withdrawing group. Firstly, we have to treat it with that. So for that, what we can take it, because we want the ethyl substituent. So you can treat it with this species CH3 C double bond O Ca. That means Friedel-Crafts acylation firstly we can do for this. So this is treated in the presence of the Lewis acid, that is AlCl3. This is gonna generate the electrophile which will be CH3 C double bond O and this positive charge. So this electrophilic will be attaching over to the benzene ring and will give us this particular species. Here we will be having is C double bond O and this CH3 group it will be present over here. Now you can do the chlorination of it, right? So you can treat it with the chlorine in the presence of AlCl3. So the electrophile Cl positive it will be generated. Now this particular group that is attached to the benzene ring, it is your electron withdrawing group and this is my meta directing. This is your meta directing group. So here the upcoming Cl group it will come at the meta position to it, right? So this particular species. Now further we can do the Clemmensen reduction or the Wolff-Kishner reduction, you can do it. That is you can treat it with the zinc in the presence of Hg and the HCl can be taken. That is called as the Clemmensen reduction. Clemmensen reduction. So with the Clemmensen reduction, basically what happens is our carbonyl group that is present here, this is converted into the carbon on both the sides and this is into the hydrogen that is converted. Okay. So here in this particular molecule you will be seeing when the Clemmensen reduction is taking place. So you will be getting here will be presence of this chlorine group, and first and then we have this CH2 and this CH3 group it will be present. Okay, so this is the procedure you can follow for this particular conversion. Now you can match your options. In the option A, firstly the alkylation they are saying. So that it is not gonna be taking place because as I told that it will be your orthoparadirecting. Right? This is not my answer. Option B, firstly chlorination and then the alkylation, again not, because chlorine group or the halogens they are also my orthoparadirecting in the nature. Right? Now in the option number C, if I see that here is the firstly the acylation has been done and then the chlorination and then the Clemmensen reduction is being taking place. So that is the correct sequence they have written. So the correct option is option C. You can cross check it with the option D as well. Firstly the alkylation, this acylation, and then they are saying that Clemmensen reduction, but that is gonna give again the alkyl species, and then on further doing the chlorination it will come at the orthoparadirecting. So that is not your answer. Alright, the correct option is option C for this particular question. I hope this one is clear. Now let us move upon to the next question, that is this one. So again, a reaction has been given. We have to predict what is the intermediate that is being formed and the final product. Okay, so here they have is this particular species NH2, and here is this C double bond O, and this OH group it is present. This is treated with the NaNO2, that is basically your diazotization mixture, NaNO2 in the presence of HCl. So in the presence of the diazonium mixture, what happens is my aniline group it gets converted into the diazonium salt. So we will be getting here is this particular species. Here there will be C double bond O and this OH group it will be present, and here will be the N2 positive, and along with that as the counter ion Cl negative it will be present. Now here you can see we can have the release of this N2 gas from the medium, and also the carbon dioxide gas can be released from the medium. So what basically happens is this OH electron density it gets shifted over here. This sigma electron density is shifted over here, and this electron density is shifted over here. That means here you will be seeing there will be the release of the nitrogen gas. Nitrogen gas will be released, and the CO2 gas. Whenever gases are being released from the medium, that reaction is highly feasible because entropy of the system it will be increasing. Right? So this is gonna result into the formation of the intermediate, that is my benzyne intermediate is getting be formed over here. So the intermediate is my benzyne species. Right? So from this only we can say the correct option is option D, because only in one of the options it is given that the intermediate formed is the benzyne one. Okay. Then this benzyne it is treated with this diene species. So here this species you are having, this is your, just a second, let us first we draw the diene. So this is my diene molecule. Okay, this is the diene, and this is treated with the benzyne substrate that we have formed it. So here the Diels-Elder reaction, that is your 4 plus 2 cycloaddition will be taking place, giving you the final product. So this species is being formed. Here this ring will be formed, and here will be this bonds are being formed, and here is this ethyl substituent that will be present. So this is gonna be the reaction that is taking place, that is your Diels-Elder 4 plus 2 cycloaddition has taken place, and here the intermediate was the benzyne intermediate. So the correct option it becomes the option D from here. Okay. So now let us move upon to the next question, that is this one. So they are saying what is the major product formed in the reaction of phenol with the bromine in the presence of carbon disulfide at temperature that is 0 to 5 degrees centigrade. So here whenever we have this phenol species and we treat it with the bromine in the presence of the CS2, that is your carbon disulfide, at the low temperature conditions. Okay, so in this cases you get is the para substituted bromophenol, the species is formed as the major one. Okay, so at the low temperature conditions your para product is the major one. Para product is major. Okay, so this is gonna be the answer to this particular question. That is your option B over here. Right? Had it been the scenario that this phenol is treated with the bromine water, in that case your tri-substituted species would have been found over here. Right? So now let us move upon to the next question, that is this one. So here the question it says is that what is the major product formed in the reaction of orthochloroanisole with the NaNH2 in the presence of liquid ammonia at the low temperature condition. So orthochloroanisole is something like this. Here we have this OCH3. This is your anisole species. At the ortho position to it, there is presence of this chlorine atom. Now this is being treated with the NaNH2. NaNH2. So what this NaNH2 will be doing is this NH2 negative will be abstracting the proton from here. This electron density it will be shifted and this Cl group it is gonna leave from here, resulting into the formation of the benzene species over here, and here this OCH group it is attached to. Right? Now in the next step again we can see there is presence of the NH2 negative. Again it has two of the paths for the reaction. It can either attack on this particular side or it can attack on this particular side. So if it is attacking on the path through the path number A, we will be getting is this particular species. Here the negative charge is formed at this particular side and NH2 has attacked over here. The bonds are remaining as it is. Right? So this is through the path A if we are following, and through the path B if we proceed. Here we will be getting OCH3, this NH2 it will be present, and here will be the negative charge. So this is through the path number B if we proceed. So here you can see the substituent that is attached is my OCH3 group, which is my electron withdrawing group. This is my electron withdrawing. So it is gonna withdraw the electron density towards itself through its minus I effect. So the negative charge, if it is formed closest position to it, that is gonna be maximum stabilized one. So in this cases you can see A is the one where this negative charge is formed at the closest position. In the B it is the furthest apart. It will be not stabilized to the maximum effect, maximum extent it will be not stabilized because inductive effect is your distance dependent. Right, here this negative charge it will be the maximum stabilized, so the reaction is gonna proceed through the path number A. Now further we have the liquid ammonia presence, so this is gonna do the workup of this, and then instead of the negative charge a proton will be coming. So meta substituted anisole you are getting this one. There will be the presence of this hydrogen species. So this is the product that we are gonna get. So this becomes my meta anisole. Any side ring. This is called as this one. Okay. The correct answer it becomes the option B over here. Right. Now let us move upon to the next question that we have is this one. Here it says what is the major product that is formed in the following reaction. Again an alkene has been given to us and it is treated with the HCl. Okay. So how is the reaction going to proceed? This electron density it will be shifted to this carbon. This is going to abstract the proton from here. So we will be getting is CH3 carbon with this methyl group over here. Here again this CH3 it is present, and here we will be getting is CH, and here will be the presence of a positive charge, and this CH2 this has abstracted the proton from the HCl. So this carbocation that is being formed, it is your secondary carbocation, right? This is my secondary carbocation. We can do the 1,2-methyl shift in this case. So this is methyl group. You can shift it on this particular side. So on 1,2-methyl shift, we will be getting is the a stable carbocation, that is my tertiary carbocation it will be formed over here. So we will be getting CH3 CH carbon with the CH3. Here will be the presence of positive charge, and here the CH with this methyl group and the other substituent it is present over here. Right? So this is the stable carbocation now because this is my tertiary carbocation, and tertiary carbocations they are more stable as compared to the secondary one. So this rearrangement it is present. Right? Now in the next step, what is gonna happen? The Cl negative that is present, it will be attacking over this carbocation species that is present over here. So final product it will be CH3 carbon with this CH3. Here will be the Cl group and here will be this CH, this CH3 and this other methyl substituent it will be present. So this is gonna be your final product. From the options you can match it now. So here I can see that the correct option is the option A only, that on this tertiary carbon center the Cl group is present and the CH is attached with the 2 methyl groups. Right? So this is gonna be the correct answer to this particular question. Okay. Now let us move upon to the next question. Again we are seeing an alkene is present and it is treated with the HCl. So here this alkene electron density we can shift it on this particular on the carbon side and so that we can get a stable carbocation formation. So basically what is happening, this electron density is shifted on this side so that a carbocation can be formed over here. So we will be getting this intermediate formation like this. Here this side this ring is present and here this substituent and on this side hydrogen we have substituted and here is the presence of the positive charge on this particular carbon center. Right. Now you can see there is a presence of the three-membered ring is present and on the next carbon center the positive charge is present. So whenever you have this type of the rearrangement it is possible that the strain from the ring it can be released, the ring expansion it takes place. So what is gonna happen? This is the alpha and this is the beta. So this alpha beta bond it breaks and this bond it is gonna be breaking and this beta is gonna form the bond with this positive charge and alpha is gonna carry the positive charge. So we will be getting this particular species formed. So the ring has now expanded to some of the extent. Here this species is present. These substrates are present as it is. Now the positive charge that is getting being formed on this particular carbon center. Right? So this ring expansion has taken place. So strain has been released over here. Strain is released. Right? Now in the next step, the Cl group that we are having, this is gonna come. Now from the above side, you can see there is lot of the hindrance present because of this methyl substituents, right? So the Cl group, it will be attacking from the below plane over here, right? So the final product we will be getting is like this. Here the substituents on the above side the hydrogen and below side this Cl group it will be present. So this is gonna be the final answer to your question. Okay, so the options we can see, A is something else, so this is not the answer. B is the correct option. Cl group is downward and the H is present in the above side and the ring expansion it has taken place. Okay, so B is the correct option for this particular question. Right. Now let us move on to the next question, that is this one. So what is the major product for the given reaction? So a reaction has been given, we have to find the product. So this we can take it in the chair form, right? 6-membered ring you are having. So in the chair conformation we can draw it. Here we are saying that OTS group is present in the below side and the above side this OAC group is present. So we can say that, or we can do it in this manner also, that on this side you have the presence of the OAC, which is something OC double bond O and this CH3 group, and in the below side you have the presence of the OTS. So this is in the chair conformation we are gonna get this substrate, right? So here you can see if this OTS group, the sigma bond is present over here. Here is the sigma star of it, right? In the above plane, this is its sigma star. Right now here this OEC group that is present, it is in the parallel position to the sigma star of this OTS group. So what can happen? This oxygen that is containing the lone pair, it will be transferred to this side. Here this is transferred to this oxygen center. Now this O negative it becomes, right? This can transfer its electron density to this sigma star and this OTS bond it can break from here. That means in the above plane we will be getting this type of the species. So here is the oxygen and here was this carbon and to this there is presence of this methyl group and here will be this double bond oxygen and this is forming the bond over here. This will be carrying the positive charge. So this is the intermediate which is formed over here. So NGP effect, basically it is taking place over here because both of these species, they were anti-position to the one another. Right? Now in the next step we have added the ACOH. So that is going to attack over here. Either it can attack on this side or it can attack on the above side as well. Either of these sides it attack is feasible. But similar environments are present, so similar species you will be getting. So let us just do this. It is through the path number A and this is through the path B. If through the path A we are proceeding, the product formed will be like this. Here in the above plane, the OAC group it will be present, and here the below side this OAC group set will be present. That means both the groups, they are present at the, one is at the, both are at the axial position we are having. If through the path B we are going, so the species that we will be getting is this one. Here the dash side the OAC group it will be present, and here in the above side the OAC group it will be coming. So one is at the wedge position, one is in the equatorial position and other, both are at the equatorial. That means we can have the diaxial or di-equatorial species can be formed. That means in the final product we can say, in the chair, in the ring form if we are drawing it, so one of the OAC group is in the above direction and other OAC is in the dash position, right? That means the trans product we are getting. The correct option you can see in the A and B elimination is being done, so that is not taking place because NGP effect is fastest among all. So that is going to take place firstly, and then the further nucleophilic attack is taking place. So the correct answer, it becomes the option C, where both the OAC groups, they are present in the trans conformation to the one another. Okay. So this is going to be the correct answer. Now let us move upon to the next question. So it is your statement based question, which says that which of the following is not a characteristic of the neighboring group participation effect. You have seen that in the NGP effect that was being shown over here, right? So the statements we have to predict which one is not the correct one. So it says, the first statement says an unusual stereochemical result, that is the true one, because SIN conformation we are getting over here despite of having the SN2 attacks. But due to the fact that SN2 it takes place two times in the NGP, the reaction it gives us the SIN conformation. So we can say that this is the unusual stereochemical result that we are getting. So this statement is your true one, right? Next is an unexpectedly fast rate of the reaction. That is also a true statement. In the previous example only I told you that elimination was not taking place, rather than that NGP effect it was taking place, because that is gonna be the fastest one. Right? So this statement is again your true one. Next is a formation of the rearranged product. Okay. And next is D statement. The statement is rearranged product. This is also the true one. Next is the D statement. It says the extent of the neighboring group participation, it increases with the increase in nucleophilicity of the nucleophile in the solvalysis reaction. Solvalysis reaction basically is your SN1 type of the reactions, right? In the SN1. In the SN1 reaction, we have the formation of the carbocation, which is the RDS step of the reaction. So this nucleophilicity of nucleophile SN1 reactions, they are not dependent upon that. So this statement is the false one, right? So this is, they are saying the extent of neighboring group participation, it increases with the increase in nucleophilicity. If we are increasing the nucleophilicity, how is gonna be the NGP effect gonna increase, right? And also in the solvolysis, generally if we say that this is through the SN1, the role of nucleophile is not there over, not present over there. So the correct option, that is incorrect statement, is the option D in all of this, right? Now let us move upon to the next question, that is this one. So again a statement based question we are having, which of the following statement is not the true about the molecules 1 and 2. Okay. So in 1 and 2 species, the first statement says the structure 1 and 2 are simply two of the resonance form of the same molecule. We can consider this statement, or firstly let us do the numbering in two of the molecules so that we can get a more clarification on this. So here the substituents that are present, they will be given the higher priorities: 1, 2, 3, 4, carbon 6, 7, 7, and this is the 8th carbon. In this case, you will be see it is the 1, 2, 3, 4, 5, 6, 7, and the 8. Right? So this is gonna be the numbering. So here we can see we are seeing that the two of the resonating forms. So in the resonating forms, whenever we are having, there is no change in the substituent's position. There is no change, right? But here you can see in the first molecule, we can see that in the at the first position and at the second position, the substituents are present. Here also it is in the first and the second position substituents, they are present over here. Okay, so we can say that these are just the resonance forms or not. Next is the structure 1 and 2 represents the different molecules. This statement is the true one because the alkene position, if you see in the first molecule, it is between the 1 and 2, 3 and 4, and between 7 is 5 and 6 and 7 and 8. This double bonds are present, but in this case, on the this substituents and this alkene positions, they are different one. So these are the different molecules, not your resonating structures. These are not there. Okay, so we can say, so these are not a resonating structure, rather these are your different molecules. You can see it. If you will be writing the UPSC name for them, you will be getting the different names because alkene's position is different over there. So these are not the resonance forms of the one another, but these are the different molecules. So this statement is the false one. Next statement, it says 1 and 2 are non-aromatic in the nature. Again, you can see that these are cyclic, they are planar, and they are following the foreign rule that is being obeyed over here. That should be for the anti-aromatic, but since the large membranes when you are having, they are flexible in the nature, so it will be having a tub shape. So, so they are not in the planar species, so they are your non-aromatic in the nature. So again, this statement is the true one. Next is the dianionic forms of these, they are the aromatic in the nature. So we can see if we consider the diaromatic species, dianionic species of this one. So here this negative charges we can consider the double bonds remaining as it is. So you can see 8-membered ring it is present. So here it is your cyclic planar. How many double bonds are present? 1, 2, 3, 4, 5. So n value 4n plus 2 pi, it is being obeyed over here. Total number of the pi electrons we are having is 10 over here. 10 pi electrons are involved. So 4n plus 2 pi electron rule is being obeyed. So that means it is my aromatic in the nature. Similarly, for the other molecule also, if you will be drawing this dianionic form, you will be getting the aromatic species only. So this statement, it also becomes the true one. So the first statement is the false one. So that is what we wanted to choose. That is not the true one. Because for the resonance, the position of the atoms, it should not change. But here it is changing. Right? So the correct option is the option A for this one. Right? Now let us move upon to the next question. Here it is saying, rank the following dienes in the increasing order of the heat of hydrogenation. Heat of hydrogenation, it is inversely proportional to the stability of the alkenes. It is inversely proportional to the stability of the alkenes. So most stable alkene, it is going to have the least heat of hydrogenation, and the least stable alkene, it will have the maximum heat of hydrogenation. Among this, we have to compare the stability of the alkenes, that is dependent upon the resonance present between them and also on the number of the alpha hydrogens that are present. So on each of the alkene species that is given, di species, we will be counting the number of the alpha hydrogens. So here you can see this is the one in the molecule A. This is the alpha position. These two hydrogens are also on the alpha position. These two are also on the alpha position, and these two, they are also on the alpha position. So in total we have the 8 alpha hydrogens are present over there. Right? In the molecule B, if we see, this is the alpha position. So two of this is the next carbon. This one is there. So this is the alpha position you are having. So we can say here there is 4 alpha hydrogens. These are present over here. In the molecule C, if you see, here is we are having, this is the alpha position. So two of them, they are present over here. Right? Next is two of them, they are present on this particular side. Right? So in total again we are having the 4 alpha hydrogens are present in this case. In the molecule D, if I see, we have this alpha hydrogens, this one, this alpha hydrogens, and this alpha hydrogens are present. So in total again here the 8 alpha hydrogens are present. So in the molecule A and C, we can see in the 1 and 3 basically I mean to say there is presence of the resonance, and also we have the presence of the alpha hydrogens. But among the A and C molecules, the maximum alpha hydrogens are present in the molecule A. So the stability, if we compare, it is gonna be maximum for the A followed by the C molecule. Then we will be having the D, because the D molecule it is having the 8 alpha hydrogens, and then we will be having is the B molecule, or we can say this is first, third, fourth, and then the second one. This is gonna be the order for the stability of your alkenes you are gonna observe based upon the resonance and the alpha hydrogens that are present in it. Now the heat of hydrogenation, if you will be seeing, the reverse order it will be there. That one, it is gonna have the least, followed by the third one, then the fourth, and the maximum it is gonna be for the second one. So second, fourth, third, and the first, that is option A we can see. This is the correct order that is mentioned over here. Right? 2, 4, 3, and 1. So this is the correct answer. So I hope this one is clear to you. Now let us move upon to the next question, that is this one. So species have been given. We have to find the hybridization around this nitrogen atom. Okay. So we can count the number of the sigma bonds and the lone pairs that are present. So here you can see 1, 2, and 1, this lone pair of electron it is present. So that means the steric number around this, it becomes equal to the 3, and whenever steric number it is 3, we have the sp2 hybridization. Right? So the correct option it will be the option B over here. Right? Now let moving upon to the next question, that is this one. So here it says which of the carbon hydrogen bond in each of the following pair compounds would yield the more stable free radical. So we have to predict in which of the cases a more stable free radical it is getting the formed. So in the pair X we see that if this hydrogen we are removing by the homolytical fission, the radicals are getting being formed, right? So this radical it will be forming, that will be here the benzene ring, and here this CH2, and here will be this radical formed here. And whereas if this homolytical fission it takes place, that will be on the benzene ring, this radical it will be formed, right? So this is on the sp2 center you are observing the radical formation, and the radicals formed on the sp2 hybridized species it is not stable in the nature, whereas if in the first case if you see this radical that is being formed, it will be stabilized because of the conjugation of this benzene ring. So among the 1 and 2, our 1 is gonna give the more stable free radical. So that means among the pair X, our option 1 is the correct. That is given in the option A and the B. In C and D, they are saying second one is the more stable. So these two options please cancel out from there. Right? Now in the pair Y, this hydrogen atom it is present on this side, that we have to consider. Okay, so in this case the homolytical fission, if it will be taking place, we will be getting this particular radical species formed. That is gonna be this benzene ring, and here will be this substituents, they are present, and the radical will be formed on this particular carbon. Whereas in the fourth molecule, when the radical formation we will be observing, that is gonna be like this one, here this species, and then the radical will be formed at this particular site, because the homolytical fission has taken place over this particular carbon center. We can see among these two again this radical that is being formed, it will be stabilized by due to the conjugation of the benzene ring. So the third one is gonna be the more stable as compared to the fourth one. So first from the pair X and third from the pair Y, it is gonna give you the more stable free radical, that is option A is the correct one. Okay, now let us move upon to the next question, that is this one. So in this question it says, see, what is the mechanism of the reaction that is taking place at the stage 1, 2 and 3. So reaction has been given. In the first step, benzene is treated with this alkene species. So how is the reaction will be proceeding? This alkene species that we are having, This in presence of the H2SO4, that is the source of the proton, it will result into the formation of the carbocation. So this particular carbocation, it will be formed in the first step. So a polar species is getting being formed over here, right? Now this is treated with the benzene. So you can see in the question, it was treated with the benzene ring, right? So in the benzene ring, this will be treated. So the substitution will be taking place over here. So this will be attacking over there. So we will be getting this particular species, and this ring will be formed and this species will be formed. Okay, and now in the next step there will be, because loss of aromaticity it takes place when the electrophilic substitutions it takes place. Now in the next step there will be the loss of this H positive from here, H positive, and this alkene species that will be formed. So you will be getting is this benzene ring with the substituted species. Okay, so this is the molecule that we are getting. Now in the next step, so the first step it is my polar in the nature. Now in the next step they have treated it with the oxygen, right? So in the case of this one, when it is treated with the oxygen molecule, so it is treated with the oxygen, it will result into the formation of the radicals over here. So you will be getting this particular species getting being formed. Here will be this radical formation, it is gonna take place. This radical species that will be found. Now in the presence of this OO and this H radical species that is present, so this one is gonna combine over there and you will be getting this particular species formed, and this substituents, and here this OO and this H species will be formed. So this is in the part number B, the substrate we will be getting being converted into this one. Now this species you have got it, right? Now the first stage we can say that there was the formation of the polar species was being formed because the carbocation formation took place. In the second stage we have seen that there was the formation of the radicals over there, right? Now in the third case, they have treated this one with the proton source. Okay, and the water is also present. So here in the reaction, you will be seeing in the presence of the H3O positive, the rearrangement will be taking place because this oxygen-oxygen bond that you are having, there is lot of repulsion present between them. So what is going to happen? This electron density will be shifted and this OH group will be attacking over here, and this bond it is gonna break from there. So this is shifted onto this particular center. Okay, so the final product formation you will be seeing, it will be your phenol species. So this is basically a industrial method for the preparation of the this phenol molecules also through the cumene species. The treatment with the oxygen is being done because the side product that we generally get, it is my acetone. So by one of the reaction you are getting two of the useful products getting being formed over here. So this reaction is used in the as an industrial method for the preparation of the phenols. Okay, so this is gonna be the answer. Now here also in this case you can see that the protect species are getting being involved. So this is again gonna be the polar stage over here, right? So the correct answer we can say in this step number third also it is my polar stage it is involved over here. So this is my polar stage. So we can say polar, radical and the polar are the stages which are involved in carrying out this particular reaction. So the options you can match it. It is saying in the first stage it is radical. So this is not the correct. In the B option it is the polar one. The second stage it is the radical and the third stage is the polar. So the correct option it becomes the option B over here. Right? So I hope this one is clear. So now let us move upon to the next question, that is this one. It says that which of the following molecule it is chiral in the nature. That means there should be no plane of symmetry present in this. Neither there should be presence of the center of symmetry in this. Okay. So in the molecule number A, we can see there is a presence of the plane of symmetry like this one. The plane can be passed. So this particular molecule it is my achiral in the nature. Right. Next again this is Br and this methyl group it is present over here. So we can see this plane of symmetry, it can be passed from this side, because bromine being in the above side and methyl will be in the downward direction. This plane, it will be cutting both of this, right? So this side they will be reflecting each other. So again, this is gonna be your achiral in the nature, right? In the B molecule, so that was the C1. In the B molecule also, this plane of symmetry, it can be passed. So this becomes again my achiral in the nature. But in the molecule D, if you see, if this plane, if you try to pass it on the Br side, this methyl group is present. So no plane of symmetry it is present in this particular molecule. So this one is my chiral in the nature. Right. So the correct option is the option D. That is, we wanted to choose the chiral molecules. Okay. So now let us move up on to the next question, that is this one. In this case, we have to find which of the following is not a meso compound. So for the meso compound, the molecules will be having more than one chiral center, and they will be presence of the plane of symmetry or the center of symmetry, it will be present in the molecules. So more than one chiral center, more than one chiral center, chiral center plus the plane of symmetry or the center of symmetry, it is present in the meso compounds. We have to look for the molecule in which this plane of symmetry or center of symmetry, it is not present. Okay. So here in the first molecule, if I see it, this one. So here we can draw it into the Sawhorse projection. So you will be getting this one. This species is present. So on the front carbon atom, that is on this carbon center, you can see at the wedge position the hydrogen atom is present, at the dash side this OH, and on this side this ethyl group it is present. Right? Whereas on the other carbon center, again this is your ethyl group. On the wedge side there is presence of hydrogen and the OH molecule it is present. So this is molecule A, we have drawn it. You can convert it into the Fisher projection as well. So you can draw it into the eclipsed conformation. Already it is in the eclipsed conformation only. So here you will be seeing OH will come on the right side. Here will be the hydrogen. This ethyl group it will be present, and on this carbon center also the OH will be on this side. Here will be this hydrogen and this ethyl group. So we can see that there is a presence of the plane of symmetry. It is present in the molecule. So this is your meso compound. The molecule A is my meso. Alright. Now we have to look upon to the molecule next of the molecules. In the similar manner, we will be looking at whether they are my meso or not. Just a second. So this is the one. So let me just take this sheet. So there we go. So the molecule B, if we draw it, you can also see it in this particular form only. That in this particular molecule, if you sit at the center of this particular molecule, you can see at the dash position there is presence of the bromine, and at the wedge position there is also the presence at in going in the 180-degree direction. We are again encountering is the bromine atom. So that means there is presence of the center of symmetry is present in the molecule. So this is again your meso species, right? In the molecule C, if we see now, so here now this one you can draw it into the Sawhorse and then you can have a look. So here we are having this particular type of the species. Here is this pH group. On the wedge side there will be the hydrogen, and the dark side is this chlorine. Here is this pH group. On the wedge side there will be presence of the hydrogen, and this is your Cl. You can draw it into the this Fisher projection. So the eclipsed conformation, Cl over here, hydrogen and this pH group it will be present, and here is this hydrogen, Cl and this pH group. So in this particular molecule you can see that there is no plane of symmetry it is present in the molecule, and as I told already that in the this Fisher projection, it is in the eclipsed conformation. We never check the center of symmetry. Never check the center of symmetry. In the previous questions that we have discussed already in the part number 1 and 2, we have encountered these type of the questions, and I told there also that in the plane, in the special projection, whenever we are having, we never check the center of symmetry because it is your eclipsed conformation. Okay, eclipse, how I have brought it around this carbon center, 180 degrees rotation you can do this. So after 180 degrees rotation, you will be getting as this species. On this side hydrogen, it will be coming here the Cl, and here will be the presence of pH, and here you will be having this Cl, this hydrogen, and this pH group, it will be this. So these are the species that we are getting. So this is not, since there is absence of the plane of symmetry in this and also no center of symmetry it is present, so this is not my meso compound. And this is what we wanted to find also, that they were asking that which of the following is not a meso compound. That means the correct answer is the option C over here. In the D molecule also you can see there will be the presence of the plane of symmetry in this particular molecule. So this is again your meso compound. Okay. So the correct option for this particular question is the option C. Now let us move upon to the next question, that is this one. We have to find the stereochemical notation for the following compounds. That means we have to find the configurations around this, right? So here, this particular molecule we are having, here is this Cl and here is this ester group, it is present. C double bond O and this OCH3 it is present, and here is this Br group. So this carbonyl species, this is gonna be the carbon 1, this is carbon 2, this is third, and this is fourth. Around the second carbon, we will be getting is the Ez conformation, and around the fourth carbon atom, we will be seeing as the RS configuration, right? So around the molecule 2, if you see, give the higher priority to the carbon, to the substituents which are attached to the carbon atoms. So here at the carbon center 2, if you see, I have one of this substituent is the Cl and other is this carbonyl. Among this, the higher atomic number is of the chlorine atom, so that is gonna be of the higher priority. And this ester group, this will be of the second priority we will be having. Now on the third carbon center, the other substituent present is the hydrogen, and this hydrogen it is gonna be of the second priority, and this one is gonna be of the higher priority. Now the higher priority groups, they are present on the opposite side, so that means the E configuration we are gonna get around the carbon. So that means around the second carbon, 2E conformation it will be there. Now we have to find the RS conformation around the carbon center, that is your fourth one. So here at the wedge position on this particular carbon center, we have the presence of this hydrogen atom. Right? So among this, you can see bromine is gonna have the highest priority, and hydrogen will be having the least priority over here. This substituent, that is of the alkene species, this will be of the second priority, and this one is gonna be of the third priority. So 1 to 2 to 3, this is in the R configuration we are going, but the fourth priority it is present at the wedge position, so the configuration it will be reversed, so it becomes the S configuration. That means at the fourth carbon center we are having as the S configuration. The correct option it will be the one in which there is presence of the 2E and the 4S configurations that will be there. Okay, so this is gonna be the answer. Now let us move on to our next question, which is this one. So this says that which of the following compounds it is gonna show the geometrical isomerism. So around the double bonds, the cis trans conformations, we have to check it. So for this, we should be able to draw the structure of these molecules. So first is your cyclooctene molecule, which is gonna look like this one, like this. This is your cyclooctene you are having, and we know that cyclooctene molecule that we are having, it can show the cis trans conformation, and its cis trans conformation is gonna look like this one. Because it is now a large membrane, it is flexible in the nature, so about its the rotations are possible, and we get the cis and the trans conformation. So here there is an existence of the geometrical isomerism is possible in this. Geometrical isomerism it is gonna be possible in this particular molecule. Right? Now the remaining molecules also we can cross check it once. So the other options that have been given to us is, that is your isoprene. So how does this isoprene molecule it looks? It is something like this one. You have here the double bond, and this bond is present over here, and this alkene species that is present. So around this alkene species, you can see we are having this CH2 substituents protein. So here there will be no geometrical isomerism possible, because the different substituents, it should be present around this alkene substituent to show the geometrical isomerism. So this is your isoprene. So in this, no geometrical isomerism we are gonna observe. Now in the C molecule, it is 2,3-dimethyl pent-2-ene. So 1, 2, 3, 4 and the 5 carbon. At the second carbon, there is presence of this alkene species, and at the third position, they have the presence of this methyl substituents. So again, you can see on this carbon center, two of the methyl substituents are only present. So again, there will be no geometrical isomerism because the same substituents are present, right? In the fourth molecule, which is 4-methyl 1,3-penta diene. So we have here is 1, 2, 3, 4 and the 5, right? So 1 and the third position, 1, 2 and this third position, this diene is present. 1, 2, 3 and the fourth position, this methyl. So again, around this carbon, this double bond, you can see two of the methyl substituents, and around this CH2 is present. So again, no geometrical isomerism is possible. So this one was the molecule number C, and this is molecule D that you are observing. So around the A molecule only, which is my cyclooctene, it has two of the geometrical isomerism is possible. So the correct option, it becomes the option A over here, that is gonna show us the geometrical isomerism. Okay. So now let us move upon to the next question, that is this one. It says that the eclipsed conformation of this particular molecule, that is your chloroethane, it is 15 kilojoules per mole. Okay, and is less stable than the staggered conformation. How much hydrogen and the chlorine eclipsing interaction work in the destabilization, whereas where the hydrogen eclipsing interaction is of the 4 kilojoule per mole of it. So we have to draw the Newman projection of it, and we will be counting the number of the hydrogen and the hydrogen chlorine interactions that are present in it. So here this is CH3, CH2 and this Cl. Around these two carbon centers, we are going to draw our Newman projection. So this is the center we will be getting, and this is going to be the front one. So this is the center. Around this, the substituents are present, and the other carbon, the substituents are present like this one. So this is the eclipsed conformation of this. So here now substituents, you can draw it on the one of the carbon atom. This is, you can say, the one carbon, and this is the second carbon. Around the first carbon atom, I am drawing this Cl group, and the other substituents are the hydrogen and the hydrogen. Whereas on the second carbon atom, three of the hydrogen atoms are present, so that we are drawing it over here. So this is the eclipsed conformation of eclipsed conformation, and they are saying that this one is having the energy that is of the 15 kilojoules per mole of it. 15 kilojoule per mole of it. And this is less stable than the staggered conformation. We already know that the eclipsed is less stable as compared to the staggered one because of the torsional strain present in it. Now the staggered conformation of it, that we can also draw it. So just the carbon positions, it will be the same, and the substituents now will be in the empty position to the one another. So in the front carbon, there is one carbon, there is chlorine, hydrogen and this hydrogen atom it is present, and on this one the hydrogen atoms are present like this one. Okay. So we have to see now how many hydrogen-hydrogen interactions we are having in the eclipsed conformation. You can see there is one this hydrogen-hydrogen interaction, and other is this hydrogen-hydrogen interaction it is present in it. So each of the hydrogen-hydrogen eclipsing interaction, it is of the energy that is 4 kilojoules per mole of it. And we are having the two hydrogen-hydrogen eclipsing interactions. Eclipsing interaction. So due to these interactions, we are going to have the energy of how much? 2 into the 4, that is your 8 kilojoule per mole of it. Now in the eclipsing conformation that you were having, the total energy, they are saying that it is of the 15 kilojoule per mole of it, right? And in the eclipsing conformation, I am having the one hydrogen and this Cl interaction and two hydrogen interactions. We have the one hydrogen and the Cl and the two hydrogen eclipsing interactions. This in total it contributes to the total energy of the 15 kilojoules per mole of it. We have calculated that for these two hydrogen interactions, the total energy it came out to be of the 8 kilojoules per mole of it, right? Now we have to find the eclipsing interaction for this hydrogen and the chlorine. This is what has been asked in the question, that how much is this H and the Cl eclipsing interaction worth? How much is of this particular value? So this you can do the subtraction, that for the hydrogen and Cl, the interaction it will be 15 minus of the 8, that is of the 7 kilojoules per mole of it. So this is the energy which is going to contribute to destabilize the eclipsing conformation that is present between the hydrogen and the chlorine atom. The correct option, it becomes the option C, which is the 7 kilojoules per mole. So this is how this question it was to be solved. Right? So that is it for this particular part now. So the next 30 questions we have discussed in this particular part now. Okay. So I hope all these questions that we have discussed so far are clear to you. But still, if you have any doubt at any of the questions that we have discussed so far, you can ask me in the comment section. I'll surely reply to that. Okay. And if you are understanding the questions and you are liking the explanation, that also you can let me know in the comment section. If something has to be added, that also you can let me know. Okay. So I hope all this is clear to you. So the remaining questions now we will be continuing from the next part. That is it for this one. Thank you so much for watching. Okay. And make sure you subscribe to the channel also, so that the upcoming parts notifications also you can easily get it.